I'll get it. Okay, check this out.
All right, let's get started, everybody. We're still going, we're loosely following along at the Judge Chapter 8. As I said before, there are some parts of the Judge Chapter are a little bit different from what we're emphasizing in class, but it gives you another take on similar issues. Next week, we're going to be going through some content that's in Judge Chapter 9. If you want to read ahead to get a sense of where we're going, that's what I recommend you read. Of course, we're still talking about categorical variables with 3 or more levels. And when we first started this unit, I sort of laid out a series of cases or examples that we'd be talking about. We're still on this first case. So when you're looking at some sort of planned comparison that could be custom, that could be something that you sort of design to match your hypothesis. Today, we're going to be talking about more about coding schemes. I'm going to introduce 2 families of coding schemes. A coding scheme is just a way of creating contrasts. So I'll be introducing 2 families of coding schemes that are fairly helpful. It's by no means the only way to approach contrasts, but I found that many hypotheses that people are often interested in can be tested using one of these 2 families. And I'll also do an extension to 4 more levels. So last time I introduced this idea of planned orthogonal contrasts. Planned meaning you're testing something that you thought of before you saw the data. Orthogonal meaning all of these different contrasts are uncorrelated. They're independent of each other. Contrast means a contrast is a way of representing means. All of these are ways of testing means, basically. I introduced the idea of mechanical variables. Mechanical variables are things that you create to represent categories. These are things that you construct in order to test a question that you're interested in. And I introduced the idea that often you have a focal contrast, which is the main thing that you're interested in, maybe your primary hypothesis. And then you have these things called residual contrasts. Residual means it's stuff that's not captured by the focal contrast. And in the very strictest version of a planned orthogonal contrast, what you want to be able to show is that your focal contrast is large, is significantly different from 0, and your residual contrast is small, smaller than the smallest effect of substantive interest. So that's where we left off. To get started with today's material, we're going to be going with a very similar scenario that we did last Wednesday. So we still have 100 people who supposedly drink vodka mixed with Tang, 100 people who don't drink anything, and 100 people who drink placebo. And we're still looking at anxiety as the outcome. But today our hypothesis is different. So before, our hypothesis was that the placebo wouldn't do anything, nor would drinking nothing, but that drinking alcohol produces anxiety. Now we're expecting that the placebo has maybe an expectancy effect. So part of the reduction that you get from drinking alcohol is due to the expectations that you bring into it. You're expecting to get drunk, and just those expectations reduce anxiety. So the effect of drinking alcohol would be partly due to an expectancy effect, and partly due to an alcohol effect. The people who drink placebo would just be getting the expectancy effect. So based on that description, what if I were to ask you, like, what contrast might capture this hypothesis, what are some ideas that you might have? So one of our groups is alcohol. One of our groups is placebo. One of our groups is nothing. If I were to put a number below each of these to represent this hypothesis, this written out hypothesis, what numbers might represent it? Well, so the hypothesis says that alcohol gives you two things. So it gives you the expectation of drinking alcohol, which might have an effect on its own. Plus it gives you whatever is in the alcohol that actually has the biological effect. Whereas the placebo doesn't have any of that biological effect, but it still gives you the expectation. So what do you think based on that? Which of these groups do you think will have the greatest effect on anxiety? Not just you, but anybody. The drinking alcohol. Okay. What about placebo? How would that compare to drinking alcohol?
Part of the social expectations.
Yeah. Great. So placebo would produce less anxiety, the same anxiety, or slightly more anxiety than alcohol.
Wait, would produce anxiety?
It would result in less anxiety than alcohol, the same amount of anxiety as alcohol, or more anxiety than alcohol, more anxiety. So whatever we give alcohol, let's just say that I'm giving alcohol -1, could be any number. The number that I give placebo ought to be greater. So let's just call it 0. What about the nothing group? Let's compare it to placebo. Would the nothing group have less anxiety than the placebo group, the same amount of anxiety, or more anxiety? Yeah, because the nothing group doesn't benefit from expectations, the expectations of drinking alcohol. They also don't benefit from the neurochemical effect, whatever it is in alcohol that's having. Yeah.
One question that came up during drill, and I could be forgetting the specifics, but it doesn't. The numbers do not have to be, like, within the range of 1 for this to work effectively.
Yeah. So I mentioned on Wednesday that there are certain numbers that are easier to work with than others. One nice feature of a mechanical variable, a contrast variable, is that it's centered. Centered means, this is kind of weird, let's see if the red does any better. Yeah. So centered means that if I take these three numbers and add up -1 plus 0 plus 1, I get 0.
What I mean is, like, within, like, the range of like 1 unit, so like alcohol being
Yeah. So the other nice feature is that it's often nice to work with what's called unit-weighted numbers. Unit-weighted numbers are, or a unit-weighted contrast is one where if I take the minimum number and the maximum number, the difference between those is exactly 1.
You don't have to do that.
You don't have to, but it can make some interpretations easier. So on Wednesday of last week, we saw how if we used unit-weighted numbers, the coefficients that got assigned to our contrasts just happened to be a series of differences. That's often the case, but we'll look at a couple examples where that's not the case today. And if you're, reading papers or looking up, doing research on the internet, you'll often see contrasts that are not unit-weighted.
And it's also not necessarily going to be centered either.
Yeah, that's not necessary either. Centering makes it so that the intercept in your general linear model will be the great mean. Good questions. All right. We've got a contrast that looks like it matches those predictions. These are, this is a way of representing the data. And as we learned on Monday, part of what contrasts do is that they take these text labels that we don't know how to work with, and they allow us to replace those with numbers, which fit right into the general linear model. They're easier to work with when you're fitting those models. We also learned on Wednesday that there's kind of a limitation to assigning numbers to these text labels, at least when we're working with 3 or more groups. And that's that that first set of numbers that you assign to these text labels aren't going to capture everything that could be happening across the different groups. There could be extra stuff, extra differences between groups that is not captured by that first contrast, by that focal contrast. So these are unit weighted values. I just divided everything by 2. It's basically the same as this -1 through 1 that we were working with. Anybody have a sense of what might be missed by that first contrast? Yeah.
Well, you can't really tell how, like it's hard to interpret how placebo is different from alcohol or nothing.
Yeah, great. That's perfect. That can be a little bit hard to see. So I'm going to show you a couple graphs that maybe help demonstrate how this might be true. So this is our focal contrast, and I've color-coded the points just to make it easier to see what's happening. What I've done here is I've just pushed up these points by 40 units and pushed down each of these points by 20 units. If I do that and then refit the model, I get exactly the same slope for that one. So that means that that initial contrast that we were working with, the C1 contrast, it's missing this case where I modify these points by twice the amount as each of these points. And on top of that, if you look at the values that I'm pushing these points up and down, it sort of seems like what's happening is I'm assigning the same numbers to these 2 points. So I'm doing the same thing to them. And then I'm pushing these points up. So it's exactly what you're talking about. It's hard to see how what's happening in the center of the placebo group compares to the average of these 2 groups. If you write that out, a unit-weighted contrast that captures that idea, again, it's assigning the same low number to these 2 groups on the sides and one higher number to the group in the center. And that's just representing in numbers that idea of making a comparison between the placebo group and the average of the other 2. If you wanted to check that these are orthogonal contrasts, they're uncorrelated with each other, one thing you can do is you can multiply the top number from the bottom and do that across the different groups and then add everything up. Somewhat easier way to do it is just to use R and actually use like the correlation function to see if these 2 sets of numbers are correlated with each other. That's just testing that these are orthogonal as we'd like them to be. To get another sense of like what's happening with this residual contrast, where I'm comparing placebo to alcohol and nothing. If I plot that contrast on the x-axis and plot anxiety on the y-axis, or startle response, and then I do the same thing where I add a large number to placebo and subtract half that from the other two groups. So I'm just doing the same thing with this graph that I did with the first one. You'll see that this line that I get, that the slope of which represents that residual contrast, it does seem to be sensitive to this kind of change. So just to make sure that we're clear, this is what happened with that first graph that I looked at. This is the C1 contrast. And this is what's happening with the second graph. So it looks like we've captured this problem that was not captured by our first contrast. Looks like we're good to go. So funny thing about this this contrast, or this coding scheme that we just came up with, is that it's actually pretty similar to the coding scheme that we were working with on Wednesday. So on Wednesday, I started with the idea that you might want to compare, say, what's happening in the alcohol group to the average of the two placebo groups. And then I said, well, we're missing that last comparison between placebo and nothing. Here, I started from the idea that there might be almost like a linear effect of across these three groups. So alcohol is the lowest, placebo is at a moderate value, and nothing is the highest. And then we found out that this is missing the comparison between placebo and the average of the other two. So I motivated these two examples in slightly different ways, but we end up with one contrast that compares two groups, or alternatively is like linear, and another contrast that compares this to the average of the two. Or another way of thinking about it is that it's quadratic. It goes down and up. Sorry. So it goes -1, then up to 2, then down back to -1. These two types of coding schemes, you can think of them as like families of coding schemes. They're broad groups of coding schemes, have special names. I'm just showing you that I'm going to be working with the non-unit weighted numbers here because they're, in this case, they're a little bit easier to understand. So all I did was I multiplied by the thing that was in the fraction. I just want to work with whole numbers here. I'll get back to what that slide said in a bit, but these have special names. One of these types is called a polynomial contrast. The idea behind a polynomial contrast is that you start from a line and then you add humps, you add inflection points. And each additional contrast adds an extra inflection point. This idea is very similar to when we went through polynomial regression last semester. You can think of it as the categorical analog. So each time we added in like x squared or x cubed or x to the fourth, that allowed us to model an extra hump in our data. Well, this is exactly, or this is very similar to what's happening with polynomial contrast for categorical variables. Each additional contrast that we add allows us to model an extra hump in our data. But in order to model that extra hump, we've got to get an extra group. So with three groups, what we just went through, we can model one hump. With four groups, we can model two humps. with 5 groups leaving model 3, and so on. Basically, polynomial contrasts are, like I said, they're sort of the analog of polynomial regression from the end of the semester, last semester. What Helmer contrasts are slightly different in that you're taking successive comparisons between one group and the average of the others. And each time you add an extra contrast, you're just allowing yourself to go through that process one more time. So with 3 groups, first you take one group and compare it to the average of the 2, and then you compare the 2 groups that remain. What happens with 4 groups is that first you take one group and compare it to the average of the 3, one group and compare it to the average of the 2, and then you get the 2 others that remain. And each group that you add allows you to do that, look at one extra level of complexity. Yeah, there's a question.
So one thing that came up was if you have 0 assigned to a group, essentially that's saying you're taking that group out of the comparison.
It's one way of thinking about it. It's another way of thinking about it, yes, sort of. Another way of thinking about it is that these contrasts are designed to like maximally pick up on one thing. So this contrast right here maximally picks up on differences between this group and the average of the 2. There could be other stuff going on in the data. You don't know, that contrast doesn't tell you. But to the extent there is that difference, this contrast will maximally pick up on that difference.
So maybe a follow-up question is in lab 1.5, you're comparing like 6 different, or like we had 6 different groups, and we're asked to show like an increase, like a 1-point increase in between each group. If we, like say it's 6 groups, if we just find like -3, -2, -1, 0, 1, 2 on, that 0 group could still be accounted for in that comparison?
I mean, yeah, so let me draw this out. So that's a perfect linear trend, right? If I erase this and moved it all the way up here, I can still draw a line right here, and it would still have the same slope actually. The intercept would change. So in a sense, yeah, what happens to this group doesn't matter, but it's a little bit more specific to say that what matters most to this contrast is the linear trend. So if I do something that modifies the linear trend, that linear contrast will pick up on it. If I do something that doesn't really affect the linear trend, it won't pick up on it. Similar principle applies to, let's say, this contrast right here. So I'm comparing one group to the average of the 2. The interesting thing, if I just move one of these down, that the average of these 2 is affected. It's, I can draw a dotted line in between them. But if I counterweight that by moving this up, suddenly the average is affected. So that's going back to this principle that each of these contrasts is sensitive to one specific pattern. And hopefully, you know, in the case of a focal contrast, that pattern is the thing that you care about most, is your prediction. But each of these contrasts is also missing other patterns that could be present. It's not sensitive to those. So to understand what the contrasts are sensitive to, you have to look at the full set of values. You can't just look at one. That actually goes back to this idea that, you know, each of these contrasts doesn't have to be centered, it just is nice. So if I added 3 to all of these and fit the model with it, that would have the same results as if I worked with this original value. It's just that it would affect the intercept. Is that a little bit clear?
Yes.
Another important principle behind contrasts is that in order to actually represent a categorical variable, each level that I add will require 1 extra contrast. So I mentioned on Wednesday how you can think of the fact that you need to represent categorical variables with multiple mechanical variables as like the cost that you're paying to represent this as categorical instead of, say, a ratio scale. Well, this is that cost. I have a categorical variable with 16 levels. I need 15 mechanical variables to represent that categorical variable. And that's a lot. So each time that you add a level to a categorical variable, you're required to increase the complexity of the model to fully represent that increase in levels. One nice thing about these 2 families of contrasts is that, I mean, they're pretty popular, they're well known, and someone's done the work for you to figure out which contrasts are orthogonal to the original one that you're interested in. It would be hypothetically possible to say, you know what, I do think that there's going to be an expectancy effect of placebo, but it's going to be a small one. So instead of, say, -1, 0, then 1, I'm going to say that alcohol is quite level. It's at -2. Placebo is at 0, and nothing is at 1. So I could heighten this difference right here, and then work out which residual contrast would match that. But you have to do some work, and it's a pretty specific hypothesis. So if that's really what you believe is going to happen in your experiment or your study, then sure, you can do all sorts of funky things with contrasts. The cost that you pay is that while they're only specific to one thing, and often our predictions are not quite that specific, at least in the social sciences. I had something pop up here about unit weighting. I want to get back to that briefly. So I'm not sure if I said this explicitly last Wednesday, but the way that you get from a non-unit weighted contrast to one that is unit weighted is you divide by this difference of the maximum contrast value minus the minimum. So for this contrast right here, you divide by 2, 1 minus 2, minus 1 minus -1.
Can you say that one more time?
Yeah. So in order to unit weight something, let's say I'm looking at this contrast, I would divide by the maximum value that I see. So that would be 1 minus the minimum minus -1, which equals 2. And you probably saw how at times I like to represent this as -0.5 and +0.5. You don't have to always do this, but there are certain cases where it just makes your interpretations nice.
How do you know what the maximum and minimum values are?
But you just look down the series of numbers, and this is the maximum, and this is the minimum.
Oh, so you just use these like tables to help you do it.
So once you've worked out, let's say that you're working out a really wacky contrast, like it's this one right here. If I wanted to unit weight this, I would divide by 1 minus -2, which equals 3. It's not a big deal if you don't remember that because there's a function in the Elm support package that'll do this for you. So as far as contrasts, I think you went through on Thursday and Friday. Okay, if not, you will this Thursday and Friday. And then there's an extra helper function that you can deal with in lab. Yeah, go.
Wait, so is unit weighting is when it all adds up to 0, right?
Centering is when it all adds up to 0.
What is unit weighting?
Unit weighting means that the distance between the minimum value and the maximum value is 1.
Okay.
So that means that when you're thinking about your coefficients and you say, okay, this is the predicted increase for a 1 unit increase in C1, while a 1 unit increase in C1 gets you all the way from the minimum value to the maximum value. So that can make some predictions easy. Other questions? So, all right, like I said, there are these two families of contrasts. And the one that we just went through, you can think of it as getting you at the top is a linear contrast. It's going from alcohol to placebo to nothing. And then you can think of the bottom one as a quadratic contrast. So it's going from alcohol up to placebo and then back down to nothing. Another way of thinking about it in this like very specific special case is in terms of the Helmert contrast, where you're comparing one thing to the average of the others and then the average of the remainder. So this contrast at the bottom is comparing alcohol to the average of placebo and nothing, and the contrast at the top is comparing alcohol to nothing. I just noticed that the 2/3 ought to be over here. I think it's just affecting the slide, but I'll fix it on the handout after class. Okay, so I'm not going to go through the full example of that particular 3-group example because it's very similar to the 3-group example that we went through on Wednesday. I just want to motivate this idea of there are different ways of thinking about your predictions. It might not matter in that one case all that much, but when you're creating these extra contrasts, the residual contrasts, that's where it does matter, especially if you have corners or more. And things get pretty complicated when you're dealing with 4-group and enough designs. I personally don't do work with those kinds of designs very much, but you'll see them out there in papers and you might work with them yourself. So to give you a sense of what this looks like, we're going to be working with slight variation on this idea of like drinking alcohol and what does it do to anxiety. So in this case, we have 100 people who drink nothing, 200 people who have 1 drink, 100 people who have 2 drinks, and an extra 100 people who have 3 drinks. So some people are getting really drunk. This is an example that I suppose you can think of drinking a quantity of alcohol as like a quantitative number. But you know, dosages might vary a lot. Let's say that you're doing this in a bar and you have bartenders who have different pours. You know, there could be very good reasons why you don't want to say that, you know, everybody who received 1 drink got exactly the same amount of alcohol. So an alternative way to think about this is that these are categories that might have a reasonable order, but You know, if you don't want to make that extra commitment, you can treat these as categories instead of a quantitative variable. We're still working with the same outcome. So our hypothesis is a little bit different. It's that each extra drink that someone receives leads to greater reduction in anxiety. So this is a case where that's pretty well captured by the linear contrast that we just went through. We're predicting that as we move from category to category, there's the same increase each time, or decrease each time in this case in anxiety. And if you look up that table that I gave you for Google polynomial contrasts, you'll find the corresponding residual contrasts. It's a nice thing of working in these families is that it's quite easy to get the residual contrasts. So once we have our corresponding table of contrasts, you can plug in this design. So we're predicting that someone who has no drinks will have the least anxiety, someone who has 3 drinks will have the most, and these two are somewhat in between. Each time you have an extra drink, you get a corresponding decrease in anxiety. And these two extra contrasts represent some of the other stuff that is not captured by that linear contrast, but that could happen as you drink extra alcohol. So it could be that the greatest reduction in anxiety happens in the middle. If you have too much, you get diminishing returns, or maybe your anxiety increases again because you start getting paranoid because you drink too much. This extra one has an extra inflection point. So it says you get the most anxiety with 1 drink, the least anxiety with 2, and the ends are somewhere in between. Just to draw it out, because I find with polynomial contrast, it's just a little bit easier to think about when you actually draw it. The linear contrast goes like this. The quadratic contrast goes like this. And the cubic goes like this. Or, let's see, linear, quadratic, cubic. So each extra contrast that we add allows us to model an extra curve. Is there a question?
No, I'm just trying to match up some of
Got it. Yeah, it should match up.
And those curves are what you were calling inflection points.
Yeah, inflection point just means that we were going up, now we're going down.
And we're unit weighting them on the bottom.
Yeah, so you could work with either the whole numbers or the unit weighted contrasts. We'll see in a little bit that the unit weighted contrasts have nice interpretations for these two, but make less sense for this one. As I find in general that when you're working with 3 groups or 1 group, unit weighting is great. If you increase your number of groups, sometimes it's great, and sometimes it's just like, I don't understand. So you'll see what that looks like in just a bit. So of course, the major difference relative to the case that we were just working with is that instead of one residual contrast, we have two. So there's two like sets of patterns that are not captured by that initial linear contrast. And that's just a general thing that happens when you add groups. Each group that you add adds one of those extra patterns.
So just to clarify, like what the residuals are like testing. So in the second one, it's just checking to see whether the greatest changes are between 0 and 1 and 2 and 3.
Yeah, that's one way of thinking about
The change in
it.
the middle is not as much.
Hmm.
And then in the third contrast, it's saying that the greatest changes happen between 1 and 2. No, yeah, 1 and 2.
1 and 2, and then 2 and 3.
No,
Oh, sorry. Yeah, 1 and 2, you're right, between these two. But we still have pretty big jumps on the edges too.
right.
I find it's easiest to think about this drawn out. So you start from a low number, you go to a very high number, you go to a very low number, and then you go to another moderate number that's more in the middle. I have some extra graphs on the next slides that maybe will clarify this. Let me know if it's still a little bit unclear. Before we go to those, I've said this a couple times, but the fact that you have two residual contrasts adds some extra complexity. And specifically when you're doing your hypothesis testing, it can be hard to determine like, okay, does it matter if this residual contrast is a large number? Does that matter for my central predictions? Just to be upfront about it, I don't have a great solution for this. I have some like general principles for you to think about and a couple thoughts about how to proceed, but I don't have a solution. I don't think this is an issue that the methodological literature has a solution for either. Is there a question? Okay, so let's say that we're working with a pattern of data that looks a little bit like this. As before, we're starting with text labels. And what the contrast allows us to do is to replace those text labels with numbers that you can, that the general linear model can actually work with. So this is one way of understanding that first contrast. You assign minus 3/6 or a half, 0 drinks, minus 1/6, positive 1/6, and minus 3/6. And then you find the line that minimizes the sum of the squared errors, given that that set of variables. You can follow the same process with each of these contrasts to get another way of understanding what they're doing. So I've assigned the same number to 0 drinks and 3 drinks, and the same number to 1 drink and 2 drinks for the second contrast. And one way of understanding this contrast is that I'm just fitting a line that minimizes the sum of squared errors, given that I've assigned the same number to the 2 groups on the edges and the 2 groups in the center. So all I've done again, I've just gone through the same process that we've gone through with most categorical variables when we've been learning it. You replace the categorical variables, the text labels with numbers, you fit a line, this is the line. This maybe allows you to see how the slope of this line will come to represent the mean difference between these groups and these groups. So that's what it represented when we were working with just 2 groups. This third contrast is a little bit funky. So one thing that I'll point out is that these text labels are in a different order than they were for the first contrast that we were working with. So 0 drinks is over here, it used to be over here. 1 drink is way out on the edge, it used to be right here. 2 drinks is over here, it used to be over here. 3 drinks is over here, it used to be over here. So I've rearranged the order, or I have to rearrange the order. I have to sort of plot the numbers as they are. That's one way of understanding this cubic contrast, is that it's predicting that the maximal effects will happen for a group that's not at the very edge, but that's somewhere in the center. And it's also predicting that the 2 groups that we used to consider on the edge will be somewhat moderate in their impact. Again, I often find that it's easiest to just draw it out like this. But this can be another way of understanding what's happening. We're sort of tinkering with the ordering of the groups when we're working with the cubic contrast. And that's generally true as you go to quartic or quintic or some of these like really complicated polynomial contrasts. Questions? Is that helpful a little bit? Maybe.
Yeah, I guess I'm like waiting to see how you interpret it.
Yeah.
It's more of my question.
Okay, so we've got a set of contrasts. We can sort of see what's happening with each of these contrasts. As with each example, we can apply the framework of null hypothesis significance testing. When we were working with 3 groups, we were working with an intercept and 2 slopes, a 3 parameter model. We've added 1 extra parameter, so we've added a 4th parameter. This is generally true if you increase the number of groups among your categorical variables. Each group that you add requires you to add an extra parameter. One way to think about that cost that you're paying for treating this as categorical. One implication of this is that there are lots of different hypotheses that you could test and that are tested if you are reading papers out there. So you could test each of these parameters on their own, and something that I'll talk about at the very end is that you can test a joint hypothesis, so a hypothesis that all of the parameters are 0. I'm actually going to recommend against that for reasons that I'll get to, but that is a very popular type of hypothesis that you see out there in the literature. Yeah.
I have a question about the model. Is this when we're just using alcohol, placebo, nothing? Or is this when 1, 2, 3 or 0 drinks?
I'm not sure if I exactly understand your question.
Like which example does this model?
The 1, 2, the 0, 1, 2, or 3 drinks. So we've got, anytime we've got 4 groups, we'll be using this model.
Well, I thought B0 was the intercept. So shouldn't there be a B4? Because we have 4 groups.
To represent 4 groups, you need 3 mechanical variables. In general, to represent a specific number of groups, you need that number minus 1 mechanical variables. So in this case, we have 4 groups. We saw that we could capture what's happening with those 4 groups with 3 mechanical variables. That leads to 3 slopes, the B1, B2, and B3. And
Okay, yeah, I think I was getting it confused with like, there were like the 4 levels, they're not like 4 different variables.
Yeah, so to represent a certain number of levels, you need that number of levels minus 1 mechanical variables. Is everybody clear on that? To analyze this kind of design in R, we follow basically the same procedure that we did for the 3-group design. So you create those mechanical variables. There are a couple different ways of doing that. You'll learn how to do that specifically in drill. You use those mechanical variables in LM. So C1, C2, C3. And you get some output. And it looks just like the output that you would get for any other linear model that you would fit. So let's go through each of these pieces of output and see how that's represented on the graph. So I've graphed C1 on the bottom. So on the x-axis rather. This C1 is represented in this slope right here. So, and specifically that 59.83, in order to interpret that, you think that's the predicted increase in startle for a 1-unit increase in C1. A 1-unit increase in C1 gets you all the way from -3/6 to +3/6. So one way of thinking about that coefficient is that it represents the linear increase going all the way from 0 drinks to 3 drinks in anxiety. So just to make sure that we're clear, the fact that I weighted this variable means that a 1-unit increase in C1 gets me all the way from the bottom to the top. So this represents the full linear increase in anxiety as you go from no drinks to the maximum of no drinks.
What if you just want to go from like 1 or no to 1?
You could change the way you represent those numbers. So you would just make sure that there's a 1-unit distance in between no drinks and 1 drink. So it'd be like -2, -1, 0, 1. You'd have to set that. But that's basically
Just reset whatever.
just multiply it by whatever numbers are required to get it to -1, -2, -1, whatever. That's something in general that's a very useful tool for working with contrasts with mechanical variables. You can change them however you want to make sure that the coefficient is equal to you. And in order to do that, we've worked with transformations in the past. This is one place where transformations really convenient. It's making sure that your coefficients have nice interpretations. So C2 is a little bit hard to see on this graph unless I draw these two horizontal lines. So I've drawn one line that represents the average of these two groups and one line that represents the average of these two. C2 represents the vertical distance between those lines. And because I've unit weighted this contrast, when I move 1 unit on C2, I go all the way from the groups on the outside to the groups in the center. So I go all the way from -0.5 to +0.5. That means that this vertical distance, or C2, represents the average of no drinks and 3 drinks versus the average of 2 drinks and 1 drink. So this is another place where unit weighting helped us. Because it just so happens that if we unit weight, that coefficient for C2 will represent a mean difference that we might care about. We could, of course, assign other numbers to this, maybe if we cared about other quantities, but this is 1 in most cases. So this is another place where the coefficient that we get from R ends up being pretty interpretable and meaningful too.
So at that point, we know that the hypotheses of with each additional drink, anxiety increases is not supported, right? Because there's a difference.
That's a really good observation, kind of. I mean, I guess my overall answer is it depends. There might be some research scenarios where, yes, the fact that C2 is significantly non-zero is really threatening to the overall research hypothesis. But I can imagine some research scenarios where that might not be the case. If we're considering this like one specific like set of research scenarios where you have one very specific hypothesis, you've picked out a bunch of groups that test that one very specific hypothesis, then yes, I'd say if you have a significant effect for C2 or C3, that's a problem. That maybe will force you to revise your theory. But research is really varied, and I can imagine research scenarios where that wouldn't be the case. One thing you can do, I guess we're getting ahead of where I was planning, but that's fine, is you can look at this graph right here, and just look at the pattern and sort of get a visual sense of like, is this the pattern that I was expecting? Well, if you really think that anxiety changes linearly with drinks, then maybe it's not the pattern that you were expecting. Maybe you would be willing to say that this pattern falsifies your theory, however you derive your predictions. But like I said, I can imagine situations where it's a little bit more exploratory. Maybe you don't have very strong prior theory, but these are specific contrasts that pick up things that you might be interested in, patterns of means that you might care about, in which case maybe this wouldn't falsify your theory. I really encourage you, if you're working with multi-group designs, to not just rely on the output from LM, but to graph your data, look at your means, really think about your theory and the relationship between your data and the theory, and whether you need to revise your theory or not. I think in complicated multi-group designs, more than many other designs, because so many different patterns are possible, you're often in a more exploratory look at research. Okay, C3 is really hard to see on this graph, and there's not like one distance that I can draw that really captures it. I think the best way to think about it is that C2 is looking at this down, up pattern with the two inflection points. If you can think of a way to draw one line that sort of captures this pattern, I'd be really interested to hear it, because I thought about it and couldn't figure it out. But regardless, this is the kind of pattern that C3 is sensitive to. It's most sensitive to. So this down, up pattern. And this coefficient value is telling us that that pattern is there in the data, but it's like, it doesn't really jump out at you from just looking at this graph right here. That's partly because when you're working with planned orthogonal contrasts, you're trying to create a set of contrast values that fully soak up all the different differences that could happen between the means, regardless of where you're doing comparison. And sometimes one of those extra comparisons, it's like, you know, if that one of those extra patterns is there, it's just not there very strongly, and so it's not there visually. That's also one of the difficult things I say with working with really large multi-group designs, is that there are lots of different ways of decomposing the results that you get, and not all of the effects that you see in those decompositions will be apparent when you look at graph. You can see with C1, generally there's like a tendency to increase linearly, but obviously the fact that these three groups seem to be about the same means that that's not everything that's going on. That's basically the interpretation that I take from both C2 and C3. There's other stuff that's happening that's not captured by the linear pattern.
So how would you interpret C3 and write it?
I'd say there was evidence of a Peter effect.
Would you say 20? Would you say the estimate?
I give the estimate, but as I was saying before, this doesn't have a nice interpretation what's the average of the outer two groups and the average of the inner two, or at least not that I can think of. I really like my centrifugal coefficients, that's why I've emphasized it. If you can think of a way to interpret this in a nice way, I'd be super interested, but I couldn't think of it. So I've already gone through some of this discussion, but this is a scenario where we've got a focal prediction or a contrast that represents our main prediction, but some other stuff is happening. And how you interpret that, it's hard to say. I'd say that best case scenario is if you've planned everything out and pre-registered some models, and you've already said in advance, I'm going to consider any significant residual contrasts as evidence against my theory. Then it's pretty clear what to do. In this specific case, yeah, I think it really depends on whether you're doing a really confirmatory test like I just described, a planned test, or whether these are four reasonable groups that you're working with, but you don't know exactly what's going to be happening. But you're still able to specify okay, the linear effect is going to be interesting, even if I don't know if it's going to be present. So is the quadratic effect and the cubic effect. I would look at this graph and say that this is not a perfectly linear pattern. And that's what the model output says as well. However, I suppose if you just pushed these points up a little bit, not even necessarily that much, I might say that the pattern does look kind of linear. So, that idea that this is not linear is kind of sensitive to random fluctuations that might be happening.
Can you check it in line? Can you check your contrast like you could other models?
Check in what way?
With the
Well,
normal assumptions. Can you check?
Sure, that wouldn't tell you if the problem that I'm describing is more about sampling error. So if you're working with a somewhat small sample, where small means even 200 participants, This pattern is going to be pretty sensitive to fluctuations in this particular mean. So yes, you could. You could do anything with this model that you could with the others. I think this problem that I'm pointing out has more to do with your whatever sample size you put into the first place. So if you, I guess that's one lesson, is if you have a very specific hypothesis, you might need a lot of data in order to test that in a powerful way. Just as I recommended with the 3-group case, I think equivalence tests can be a nice tool for testing this kind of focused hypothesis. So you might, for example, do some simulations in advance to see how much deviation from the linear effect do I need before I see a pattern that looks like it's counter to my theory. Use that to specify the smallest effective subset of interest, and you test whether the effects that you got are smaller than that smallest effective subset of interest. That's just the answer that I come to when I'm thinking about this, but again, it's not something that I can't put to a paper that makes that recommendation. That's just something that makes sense to me. So one way you could go about this is set a smallest effective subset of interest for C2 and smallest effective subset of interest for C3. One way to do that is through simulations, but it would be a little bit involved. That could be one way to cope with this problem. I'd say there's not like one great solution for it. Okay, so we've gone through a couple different categories of coding schemes. The Helmholtz contrasts and some polynomial contrasts. And I've shown you how to make the extension to corporate designs. We're by no means done with the topic of categorical variables with multiple levels. So I'll show you more examples, walk through more examples of these categorical variables and other ways of analyzing them. So we're definitely not done. I did want to cover a couple loose ends, though, that are somewhat related to orthogonal contrasts, but they're also like a little bit independent of them. By the way, I remember that there were a couple questions, like I think you asked a question, why not just compare two groups without considering the third? I decided to talk about that on Monday because it fit better with the plan for that lecture, but I am remembering those questions and I'll get to them. So when I went through that, when I've gone through that null hypothesis significance testing slide, I mentioned how there are multiple different hypotheses that you could test based on the same statistical model. And I talked about all of them except for this one. It's a joint test, where joint means that you're saying that all of these things are true. So B1 will equal 0, B2 equals 0, and B3 equals 0. And one feature of that joint test is that if any one of those conditions is not met, then you're rejecting the null hypothesis. So just one of those things has to be true for the null hypothesis to be rejected. This is actually a very popular way of handling this kind of categorical design. This kind of test is often called an omnibus ANOVA. Sometimes you see the term one-way ANOVA, or 3-factor design, or 4-factor design. All of these are depend on this one kind of test primarily. One way to do this in R is you fit the compact model. So the model where B1 is equal to 0, B2 is equal to 0, B3 is equal to 0. And then you compare it to the augmented model, which is the one that we've primarily been working with all of the contrasts in the model. And then you compare them. So you compare the sum of the squared errors. That gives you an F value and a P value. So if you wanted to do that, this is how. We've looked at this kind of hypothesis test once before when I first introduced regression with multiple variables. I didn't spend a lot of time on it because I'm not failing this kind of test. But we have looked at this. And usually in an omnibus ANOVA, one-way ANOVA, if you can reject the null hypothesis here, you then follow it up with S-specific contrasts here. The reason that I'm not a fan of this method of hypothesis testing, at least in the case that we just described, is that we're talking about a case where your hypothesis is captured by a single contrast, C1. And in fact, you specifically assign numbers to C1 that are maximally sensitive to your hypothesis. And yet, when you do this test, you're diluting the effect of C1 with the effects of the residual contrast, the contrasts that maybe falsify your hypothesis, which seems a little bit weird. You're diluting your main hypothesis, your focal hypothesis, with stuff that, if true, would actually, like, you'd call that falsifying your hypothesis. Like that logic doesn't make sense. And in fact, just to show you that this is true, if you consider this F value versus these three F values, that F value for the omnibus test is literally the mean of these three F values for the contrasts. It's literally the average. So if you've got very low F values for C2 and C3, let's say they're close to 1, meaning you cannot reject the null hypothesis, that gets averaged into the F value for your focal hypothesis. That's pretty weird, or at least I think it's pretty weird. And this will decrease your statistical power, your ability to reject the null hypothesis if it's false. And the hit to power becomes even more pronounced as you add extra groups. So in a 5-group design where you've represented your focal hypothesis with C1, you're averaging the F value for that C1 with 3 other F values. If you're working with, say, 19 groups, you're averaging F1, C1 with 17 other F values. And again, to me, this doesn't really make sense. I'm going to get back to omnibus ANOVAs because there are different functions that they could serve. I think they're generally better tools in most cases, but I'll get back to this idea later on in this unit. One last note is about graphing. I didn't have quite enough time to tinker with this graph to make it prettier, but my main message is that you have all the tools already that you already need in order to make graphs with this kind of design because you've done 2-group designs. And generally, I think the tools that you use for 2-group designs work perfectly well for 3-group designs or 4-group designs or 5-group designs. There are extra enhancements you can add to graphs like this. For example, sometimes you see a horizontal line above groups that are being averaged together, and then a little like a t-value or something that shows, hey, these 3 groups, this t-value is the t-value to the average of these three groups versus this group. So sometimes you see call-outs on local hypotheses. I'm not going to require you to do that. There are ways to do that in R. There are ways to add text and lines to slides. That's what I'd recommend you do if you wanted to have that kind of enhancement. You can also do it in any sort of specialized graphical software like Inkscape or there are lots of them. I'm going to add a writing summary so that you have that as a reference for whenever you use it analyze this kind of design. The big takeaways are that there are two special families that I think cover lots of different kinds of hypotheses that you might be interested in. That's not the only way to make custom contrasts, but they're handy to know. In order to represent categorical variables that have lots of groups, you need mechanical variables, so number of groups minus one. Interpreting residual contrast is pretty tricky, and that's an unresolved problem. I'm making the case that anonymous ANOVA is kind of a not very powerful way of testing these focused hypotheses. Thanks very much. I'll see you all on Monday.